So good morning, good afternoon, good evening, everybody, and welcome to this week's EMinar. I see people are still coming in, but I think we can slowly get started with the introduction. So today we have Stephen Hallinan talking about MT in natural resource exploitation and his experience as a contractor and what has worked so far. Before we get to Stephen's talk, the typical introductory stuff, I assume by now that, well, you've registered for this, that you know about the MTNet site and where you can see also the future EMinars and how to register for them. I suppose for those of you who watch this on YouTube, this is your resource for other EMinars and what's going to happen throughout the next year. Also, just a quick reminder on how things work. If you haven't been part of a Zoom webinar first, I think the main thing is that all questions should be raised through the Q&A button, preferably not through the chat. If you really want to talk, you can raise your hand and we can give you permission to speak. So far, we typically had all the question and answers at the very end, and that has worked fairly well. But yeah, if there's something you really want to know or discuss while the talk is ongoing, then please raise your hand and I will alert Stephen. I will monitor this and sort of convey your questions. And yeah, a little bit of background for Stephen. So he has a degree in geology that he did in Dublin, and then did some geophysics in Costa Rica and some postdoc work in gravity, mostly in southern Brazil. And he joined Geosystems in 1994, and I think went through the different corporate changes, sort of when it became Western GECO and then Fugro and then CDG, you know, all those things he participated in, and is, yeah, a non-seismic geophysics, as they like to call it in the hydrocarbon game, specialist, and working with the CDG multi-physics imaging group, working on EM and in the combination with gravity magnetics, seismics, and other methods for oil and gas, mining, and geothermal. And finally, a reminder about next week's EMinar. So we have Hannah Peterson talking about combining land and lake bottom MT data to study volcanic systems in the Mono Basin in California. So back to a slightly more academic topic. And with that, I'll stop sharing and hand over to you, Stephen.
Thank you very much. Give me a couple of seconds to get some material up on the screen. So we start every seminar with a question, can you see the screen? That's what come through, okay, Max? Sorry.
Yep, all fine.
All right, very good. Now, Alan, you'll be glad to know I left in the complete MC Solutions sponsorship message at the bottom right there on this slide. But I do want to thank Alan and Max and everybody for the invitation to do this. And it's taken a while of haranguing and so on to get here. And it's been a long time in this business, and what you're going to see is a bit of a dog's breakfast of some things we've tried, some things that have failed, and some reference to many of my colleagues' work. And I suppose we ought to start off with some kind of a statement, you know, about what it's like at this end of the business, in the contractor's end, and not maybe in the familiar academic sphere, but it really is a continuum between academics and what we do, and we employ several of both. So, but this is the kind of reaction you get when you turn up at a company and you start talking about MT, and they just look at you as, well, you know, we're expecting to hear about seismic, and it gets even worse when you start talking about the origins of your sources, and you say, well, it's a sunspot activity, and it varies with time, and it's, you know, and that people at that point usually start leaving the room and moving out the door. But it's a lot of that is, I guess, a function of how we're used to talking about MT within our own community, and I mean everybody on the line, as opposed to people further up in the management chain. And what we're going to try and portray today is the kind of efforts we've been making, and in parallel with many of you, of course, are working on the same things, to try and get answers that make sense at a boardroom level. I suppose it was trying to find a way to phrase what does it mean by, you know, working on the commercial level. At the end of the day, somebody's got to make a decision, usually a drilling decision, and that is usually a meeting held without any geophysicists in the room, let alone multiphysics or non-seismic geophysicists. Geologists, yes, because they're exploration managers, because they need some sort of concept of what geological model they're going to use for that drilling decision, and then it's their geologist's interpretation of what the geophysicists have come up with. And we complain about that system, but that's just the reality of it. And so everything we do has got to be something that makes things cost efficient, but also meaningful further up the chain. So not just to the geophysicist who might be your end client, but further up the chain in this sense. Just a quick word on CDG Today and where we are. Thanks, Max, for the introduction. You did right. We are on CDG Today, and we've managed to get Milan even on the map in this clustered area in Europe. But there's a huge spread of people across the globe. There are three main hubs: one in Paris, Houston, and Singapore. And the dominant element today within CDG is in geoscience, so data analysis, huge amounts of data, huge compute power, and a lot of smart people, which is nice. We don't any longer carry out data acquisition, and that includes all the the multiphysics stuff that we used to do. So we're entirely focused on processing and modeling of data and interpretation, of course. Now, we work with quite a lot of these, and we'll get to some of that as we go through the talk, maybe, if I can remember. But we're not really just a standalone group fighting for our own cause. We're very much part and parcel of a new group within CDG called the Energy Transition and Environment team, and that's growing. And so there are geothermal businesses in there, there are mining businesses and so on. And while we carry on, of course, as part of the transition, as you would expect, there's still a focus on hydrocarbons. It's recognized that there are many things that we can do in the geoscience world, which of course are applicable to the energy transition and environment space. So what do we do in CDG multiphysics? This is now the preferred term. Non-seismic is just kind of, it was too negative for years. We tried for years we now tried to call the seismic people non-multiphysics, but that hasn't caught on yet, but it may do one day. And as I mentioned today, this is what we're doing with mostly processing and depth inversion modeling. Pretty much all the work we do is in 3D. All the services we carry out are in 3D, but we do involve obviously 1D and 2D as part of the testing and arrival at those 3D solutions. So for quick solutions or interim preliminary results and so on. And we cover a huge range of different data types, so like ground data, airborne data, marine, whether that's seabed nodes or shipborne streamer nodes, and so on. So that's CSCM data or shipborne gravity meters or whatever it is. And we do quite a lot of feasibility modeling and survey design, training as well. Although we get a lot of academics and others consultants involved for some of the training programs we do. Electromagnetics is, I suppose, our core business, and we've added the gravity and so on around it, partly because of some of our backgrounds, partly because of the demand. And there's simply a lot more gravity data around the world than there is other types of data, magnetics, of course, too. Airborne data, we get involved in a lot, frequency and time domain. And that goes too for the ground data and the marine data. Travel time tomography has come in recently, and I suppose it was sparked off by an initial effort to try and get involved in the oil and gas space with, around salt domes and refraction seismic. But really, it came about because it's used a lot in geothermal, and in high temperature geothermal areas. Of course, there's a lot of micro-earthquake activity already, and then when you start changing the reservoir, then you induce a lot of events too. And this is fantastic because you don't have the problem of typical reflection seismic, which doesn't work terribly well in those terrains. It's also very expensive. And here you have your sources directly below the targets and so on. So it's an excellent method. So we've got involved in that. And we've added that to Randy's code, along with gravity and magnetics and all the other things, all in that code. So I suppose about half the people we have, more than half actually now, including some new people coming on board in these weeks, are involved in the software development side. And many of our geophysicists get involved in some part of the software development too, whether they're scripts or Python codes and so on. So it's a huge part of what we do. The two main 3D codes many of you will be familiar with. There's Randy's code, of course, RLM3D, and then there's ODSU by Carsten Scholl, and they've somewhat come together, at least the inversion side. And there are many things they have in common. And they are different. Carsten's code, for example, handles the time domain, Randy's not, and so on. And a core development we have is this GeoTools package, which we're expanding all the time. So I guess that's a lot of the effort is to get all the other elements eventually within GeoTools. So the kind of things we talk about today, you'll see will be in there as well. And then we have a piece of software outside that 3 space, which is where we do, it's written originally in Python, that's being updated and being used actually across CDG in various parts of it, because it's an excellent way of visualizing. You see some images at the top right. For example, these are all out of 3 space, whereas the one at the bottom is from GeoTools. And that's expanding as well. And I want to make the point that, this talk we're giving today is really a we. There's very little of my effort in it. My role is simply to bully people into making things as geological as possible and try and make the numbers, at the end of the year. But we've been working together with many of the people in the current team for a very long time. And I joined Don's group in Milan in 1994, and others that are here today and did very much a core part of this business have come along the way as well. Ephraim, Randy, Wolfgang, Federico Lice, Carsten, Stefano, and Mauro, who's driving now the GeoTools team. And there's now 4 other people involved in that. 5 now, sorry. And then, of course, many others who are no longer working with us, but we still employ with consultants. It includes Don, of course, and Peter. And I would, of course, like to mention also Sylvia Forrest, the late Sylvia Forrest's huge contribution to all of this process, right the way through to a few years back. Okay, we do obviously services and we license software. And we thought that was a hugely, clever thing to do, because we would have more time to do projects and selling the software would be fine. But of course, once you let people have your own software, you get lots of requests to change the software and update it. So there's no such thing as a free lunch, as people say, and that's entirely true in our business too. But it's given us an enormous amount of feedback from various users doing different things to what we do. So we learn a lot from it, as well as it being a business. Now, what the map shows here are all the MT projects or MT related projects. So they might have MT in gravity, or there might be MT along with marine CSEM, the red ones. And you can kind of guess what the red, blue, and brown mean. So the red ones are projects that we've carried out for the petroleum market. The brown ones are for mining, and the blue ones are for geothermal. And as you can probably tell, we have quite a lot of activity on either side of the hemispheres. We sit in the middle. So our day starts with phone calls in Australia and New Zealand, if we're really unlucky. Indonesia and so on, and then finishes in the evening with screaming and shouting with people like Alan in Canada. And Randy sits over here in San Francisco and so on. So it's, you know, huge different environments and different markets. And I suppose the one that's growing most at the moment is, of course, mining, and that's all thanks to the need for natural resources for the energy transition. So everything that comes from, you know, MT is particularly used for copper exploration, but also in other things. It's busy also in geothermal, and there's still clients of ours in the marine CSM world in oil and gas, but also MT and other methods as well. So what have we done with an MT focus? Looking at this, these are some numbers we did a parse through some directories, and thanks to Wolfgang for helping with that, and some counting by others. So we did acquisition of data from 2000 in the present embodiment of the company from 2011 through to 2014. So over the space of about 3 years in total, we started very late 2011 and finished about mid 2014. And that was about 44 projects, and there are over 4,000 MT soundings acquired during that time. MT processing we did then, of course, but we also carry on doing it, and we have a lot of projects for doing reprocessing of other data, particularly in noisy environments. And we'll see a bit of that in a minute. And then we see a vast amount of data from 3D MT inversion projects. And those that are joint inversions with MT involved in them, there's about 31 of those. So the vast number of the projects that you see on this screen are have a component of 3D inversion in it. So I suppose that's our, you know, our main project. And when it comes to MT, of course, that means that's Randy's code. And as you may well know, we're also looking for somebody to join Randy, who's busy interviewing people later today. So moving on from that, I'm just going to go through a few aspects of things we've done. And like I say, these are kind of pulled out of the air over the last week. Things that we thought were interesting that might be shown. We can't show obviously everything we've done, and oddly enough, the things that don't work are the ones that are easiest to show. So there might be a focus on that, and that may be a reflection of my slightly cynical side as well. So this isn't by any means I hope a plug for the kind of things to do, but a view of how things work in a commercial arm for this service companies, and what directs our research efforts. All right, so very early, this was the first survey we carried out in Mongolia in 2011, again in the present company. And the whole point of this survey was it needed to be extremely efficient, because of course local logistics were quite expensive. So we had to come up with an efficient way of acquiring the data. So we just bought the equipment, and our infinite thanks to the client who trusted us to get on and do this. And we had 3 crews working out of vehicles on not entirely flat, but fairly flat terrain, a few hills and so on, a bit of snow on the ground, and 3 instruments per team. And they recorded 3 AMT during the day, which were basically leapfrogging along, and then 1 was left out overnight. So one of the 3 that was an AMT site was then moved to an overnight one, and the others were picked up. And so they were recording 36 sites, 36 new MT soundings a day, and the frequency range, even for those recorded during the daytime over 2 hours, went down to about 100 seconds, right the way up to 10,000 hertz. So these are broadband 5-channel, 5-component stations everywhere. And we thought that was fantastic. The people who were in the field office didn't think it was great, because processing that number of stations a day was a nightmare. And although there were 2 people there and some assistants from Milan putting the curves together, it was a real struggle to keep up with that. So while we thought we were smart at the time, Peter, I don't think will ever forgive us. But anyway, that all worked out quite well. And the data that came in there really wasn't an enormous difference between the MT that was recorded overnight and the AMT during the day. The biggest difference, funny enough, was actually in the higher frequencies, not at the lower end. The just weaker signal at the higher frequencies, fairly consistently for that data set. Otherwise, it was pretty clean. There was some industrial noise. There's an existing mine site at the area. They were busy building another one, so there was plenty of electrical energy around. So talking about the processing side, from the beginning we made an agreement with Jimmy Larson, and he gave us exclusive use of his code for commercial purposes right from the outset. And we didn't make any great modifications. We had some back and forth at the beginning, and Jimmy very kindly has let us keep using the code, and we fund some university activities as opposed to a license fee, and that agreement seems to work out very well. Anyway, Jimmy, if you are listening, it's still extremely useful. I'm not going to go into details of what the other, the standard processing is. It doesn't really matter. You've seen the kind of thing that happens. And in this environment with some average noise levels in the data, the Larson processing works extremely well. And we've relied on that for years. There is a message, of course, in this, which is somebody needs to do something else, and I'm sure you're all working on it, but we'd love to hear more. Now, that's in a normal environment. Things are getting noisier and noisier, and we will be working around mine sites and industrial areas more and more. And the reaction in the past has been, well, we'll just do CSAMT and forget about it. And we can now model CSAMT. We're not going to talk about that today. We should be, but that's not part of the talk today. And we're going to release that during 2022. It's already been worked on. You've probably seen some publications on it a couple of years ago. But if the other arm is to come up with a better processing code, a modern one. Now, this was tried in Italy. It's a different story. The geology is quite complex. The important part here is that there are resistive carbonates, sometimes outcropping as part of the geology there. So you've got this extremely efficient way of spreading the electrical noise, wherever that comes from. And the other issue in Italy, of course, you've got this area is directly between two of the main high-speed electric train lines. So it's been a real struggle to get data below a second. You can kind of get data down to about 3 seconds, as you can see here. And then beyond that, it's always a bit of a struggle. So again, thinking we were very clever, and which is always a good way to set yourself up for defeat. We had a crack at doing a few different things, and I'll just go through some of these. Some of these might be quite fun to see. They were depressing at the time, but they're quite funny looking back at it now. So that's the typical processing as we've seen. It's fine, still noisy, and no great surprise there. The train lines, the blue lines and purple over on the right, and the red lines here. And then there are endless power grids and so on. And there's the MT survey, beautifully positioned. It's almost like it was designed on purpose in the middle of that. And then along with the train lines, of course, there are all the usual power stations and so on, and the substations there. And we threw a lot of people at this, including some colleagues of ours who were working for EMET. EMET was a Russian company, St. Petersburg Marine EM normally, but they also had exceptionally talented people with EM background, and a few of them came to the office, and then we sent them directly down to Tuscany to try and sort this data out, because somehow somebody will have a bright spark and realize what to do with it. And the local people were quite concerned because they couldn't understand, why were Russian tourists going around taking pictures of all the electrical installments and so on. So it took a bit of explaining, but they were very patient in the end, I have to say. Now you can imagine the kind of things that go on. I know Alan at least looked at some of this in South Africa many, many years ago. I don't know if it's similar to this, but it's a nightmare. And you have these DC shifts, you have enormous, if you think about the line is live, and during that live section, you're essentially putting, the train is returning 20,000 amps into the ground and on rock, you know, with carbonate. There's a bit of a veneer of cover, and then there's the carbonate section below that. It's pretty hard to see anything through that. So we deployed 2 far remote stations, thinking, you know, one might fail, or we could somehow come up with a way of using them both. One in areas where we'd surveyed before. So one was in northern Greece, where there's a nice sedimentary basin. It's obviously in a completely different electrical scenario to Italy, and away from the train, and there's a nominal conductor in between the two to soak it up. So we thought these are about 800 kilometers away, each of those. The other one was on the island of Minorca. That was slightly less successful. It's quite a noisy island, and again, fairly resistive. Anyway, we tried all kinds of things. So this is the conventional processing, if you like, using a sort of local remote. And that's fine for the data down to about 1 second, and then it falls apart. As you can see, the usual curves take off to 45 degrees north. And you get the same thing if you process it with the far remote, although you do push it out a bit further. So you got maybe half a decade more of reasonably reliable data. And we tried various things. There's the first one, as you've seen before, with the remote. ES is Spain. That's using that remote. This one is using the same, but with a slightly increased consistency, using time segment selection. So, you know, the old-fashioned way of going through the time series, picking out the segments with higher or higher coherencies and slightly less noise. Single site processing, again, same thing. Then combined, this was combined using various different methods and coherency tests and so on. And at the end of the day, okay, great, you might convince yourself that you could get out to 10 seconds, depending on what data you pick on that, but it's clearly, you know, still got some issues. And we tried again in a multi-run. This is different types of coherency runs and so on. There were literally 6 people in the field office for, I suppose, you could hardly call it a great return. So then we thought, well, if we knew where the train lines are, maybe we just treat it as this vast, albeit moving at 300 kilometers an hour, remember, some of them, and then the freight trains at night are obviously slower. A vast source. Could you do something with it and use the transients? And again, a lot of time was spent doing this. You've got the train monitors. So we set up a station next to the train line to make sure we were measuring the same thing. And lo and behold, at a site in that survey area, you can see the effects of that. They're slightly smoothed out, of course, because it's the way that diffusion works. And then you have the MT signal on top of that. You can kind of see bits of that in there, but not immediately obvious, I suppose. And we tried modeling it as a transient with a source and a line source and so on, and trying to figure out where the train was at what time and all the rest of it. And let's just say it was a kind of work in progress, and it was interesting, but we interrupted it. Obviously, when we got out of the data acquisition business, there didn't seem much point. There were other things we could spend our time on. But I suspect, you know, that there would be a way to push this a bit further. But you may find that the problem isn't just the trains on its own. There's also the direct interference, of course, of all of that signal with the rest of the electric power grid, and how those combine to produce essentially coherent white noise. Okay, enough of that. Static shift, we've been bleating on about this for years. Of course, we're not the only ones, but we had a chance to try and explain it. You know, again, these things are often discussed thoroughly throughout the academic community, and we get a lot of our input from that, of course, but they're not necessarily easy to explain to people in industry. So forgive me if this is a little simple, but we were working in this terrain on the left at the time. This is a project for gas exploration in southwest Bolivia, and we'll see this again later on. And when you forward model that and you produce essentially a TM mode. Look at the apparent resistivity at 10 seconds for that. You can see the kind of things that happen. You've got highs and valleys and lows on top of the mountains, as you'd expect. Previous people, of course, have worked on this way back, Hallinan and Homan and so on. Everybody's familiar with this. We increase the size of the loop, or the blob, sorry, to about 100 by 100. And you can see a fairly significant static shift. You've also got some effects at much higher frequencies, but the classic TDM approach here would work. But that's, just for that case. If you're in rugged topography, and here's a true topography example with a vertical exaggeration of ×2, but that's the kind of terrain we were all working in, heaving MT equipment up and down and so on. So we take that and put it into a kind of simplified ridge model and do some MT modeling, but also, of course, time domain to see what happens to a time domain loop, because everyone's saying, why aren't you measuring time domain with all your MT? And it's just, when you're in that kind of mountainous terrain, carrying all that extra gear around is an absolute nightmare. Commercially, it makes no sense if you can deal with it through some slightly more illuminated processing or modeling. All right, so you get the picture anyway. This is a 30-degree slope, and you see the usual responses in the TEM, TM, TE modes. I'm guessing this was done back then. This would have been done in 2D. The TDM modeling, however, was done in 3D, and we see that here on the right. And thanks to Carsten for carrying this out. So the flat Earth response is the green one, and it's reasonably flat, as you would expect. Then there's the response for a 30-degree slope there, and the response for a 60-degree slope. So the bottom line is, if you're going to be relying on the TDM data, which is itself measured on a slope, to then correct for some static shift, which is a kind of rude bucket for a whole mass of different problems, then you're in trouble. And you see this response here on the left-hand side. Now everybody's familiar with seeing data. It got up to 10,000 hertz, as you see on this one. But if you cut that back and you only look at it to 100 hertz, which is where we used to be at the time, you see this difference between them. Of course, it's not a static shift; it's simply a response from the topography. So shifting it would make absolutely no sense at all. Anyway, what seems obvious now was not so obvious to everybody, at least then. So here are a couple of sections through these 2D inversion sections using different static shift strategies. The straight Earth model on the left, and we're inverting for is essentially the one that generates the synthetic data. Now, if we invert it in B using the frequencies with no static shift, you're applying no static shift to the data, then you get back, lo and behold, the same model. You do have to believe me that that's inversion output, not just a copy of A. But anyway, down in C, it's slightly more interesting. This is the same as with B, but now we've only used the frequencies up to 100 hertz. All right, so there's nothing that tells the inversion that the data, come together or whatever. There are no inputs for the very near surface part, and so it's trying to compensate for the gaps it sees with structure. So that's a mistake. And D then is the same as that, but now we've actually committed the crime of static shifting the data using the time domain response in advance of doing the inversion. And now we've created an even bigger anomaly, and this now starts to look like structure. So you can see the kind of thing that happens, but it's entirely coincident with where the topography is. And in this case, the static shift is indeed only considered as a cause from the topography. So that's where we were then. That was back in 2012, published in 2013. There are many other causes, and this was some work that Wolfgang, Randy, and Federico did later on. And we published that twice, once in China and then at the EAG. So there were several different causes, of course, not just the there are galvanic effects, there's the site positioning effects, of course, and we've examined those in later publications as well. And then there's, modeling inaccuracies. So if you're using a coarse mesh, or as you see at the bottom here, or a more detailed mesh above that, you get a different response just because of that. So there could be many effects. And what we're going to examine now are, as it was examined then, are the effects from galvanic distortion. So that's what we saw before, the kind of thing that used to be done with an empty TDM response, correcting it and so on. That's politely data manipulation, not good. Just not, there are joint inversions as well of that, but it's not considering the assumption, underlying assumption is that TDM is just fine. And it's a 1D response and so on, which of course is not true. It has its own issues. Now then in 2 and 3D modeling, there have been several efforts to do it here, and particularly applying the complete 2x2 matrix that you need. And our implementation looks very much like the work that Anna did and published in 2015 with others. So, we all know this now, but I mean, manipulating data, of course, can be dangerous. You're going to be present on the calculated data as well as the observed one. Asking the inversion to fix everything, all the evils that you've committed, at the input data is also bad. You can also, try and reduce modeling errors, and that's not a huge issue today. Build a finer and finer mesh, and of course there are lots of other ways of coming up with fine meshes and meshing schemes available along with the one that we have. And what we're going to see now is, I'm not going to go through this, as you can well imagine, but you're all familiar with this is basically how we did it for a synthetic model, where you're using the entire 2x2 matrix. Now, essentially, we apply that to the synthetic model, where we've put in a lot of conductors. These are not distorters themselves, of course. These are just targets, and it's inspired by a kind of geothermal case, if you like. So where we see a broad resistor below a conductive unit, and there may be several different conductors above it. They're obviously box-like shapes and so on, but it's not terribly important. The question is, what happens to those when you distort the data with some galvanic distortion, and the effect on the inversion of those bodies, what that would be. So we apply the distortion using Green-Bailey method. We simulate the distortion there, and then we carry out various inversions on with and without. We've applied some Gaussian relative error to that as well. Now let's see if we have a starting model for the inversion. So it starts with a half space of 50 ohm meters. All right, so here's the synthetic data. This is the undistorted data. This is the kind of thing you would recover from those synthetic data without the distortion, just having applied some Gaussian noise. And that's a reasonable job. Seems to recover that in the right place, which is always refreshing. And now when you look at the distorted data, but you've not included distortion within the inversion, it's trying to fit the inversion now, fit the data with an inversion that includes a lot of structure to account for those distortion efforts in it. You can see all these tiny effects within the inversion result, both in map format, particularly near the surface, and here. And just compare that with the earlier one, right? That's the real one. And this is the one with the distortion included in the inversion. And now if we include an inversion for distortion, including that matrix in the inversion process, then we come up with a model which is fairly similar to the result. So we're including it today because this is used in a lot of the inversions that we run. It's pretty much essential. Here are some of the plots. You can imagine this is the undistorted data. This is what happens with the distortion added to it. and the results from the inversion without the distortion are plotted as the lines. So the data are the dots, and the response from 3D models are the lines. You also notice that the RMS, of course, is much higher in the case where the distorted data is not taken care of. And then, in addition to that, you need some constraints. Not only are you doing this so-called C inversion, but also the regularization of the surface needs to be weighted accordingly. And so in all of these parameters within the inversion, you can apply different weights to how you want to do this, whether heavily or light, where the distortion has some direction in it. And obviously, if you apply some smoothing out of the near stuff, that also helps. So here's an example on some real data. This is the Dirajet field, and we've worked with Star Energy here for many years. In fact, I started working there in 1996, I think. And we'll look at some MT, and this is a 3D inversion of MT in an area we were fairly familiar with. Just taking the data and inverting it without considering distortion to start with. And you can see some lumpiness in the inversion results. This is 50 meters below the surface. And you can also see some fairly poor fits here within the data themselves at some of the stations that are near these boundaries. There's quite a lot of topography here, but there's also other things going on with clays near the surface. So I should have mentioned that. Obviously, being a hydrothermal geothermal area, there are lots of very conductive clays, and they're in pockets. Some of them get eroded away, some not, and so you get a considerable variation in near surface resistivity. So you see these sort of odd features between MT stations up here, and we'll see a blow up of that in a minute. Now, if we run that same thing, but considering the distortion, we get a similar model below the conductor, as you'd expect, but it's quite different shape now to the conductive body itself. And this is encouraging. It's taken away the need to get people also the interpretations made of very near surface anomalies, which of course are not reliable. So we get a better fit. It's enhanced near surface continuity and no loss of detail at the depth of interest. So it's not like we're smoothing it out at depth. Obviously, the main target are these. What's the shape of the base of that conductor in a geothermal system, which ultimately provides you with information about where the area is most productive below it, and highest level of convection, vertical permeability, and so on. Okay, so there's a blow up of that. So the ratio of the two inversions on the left-hand side, you can see where the most changes are the dark blues and dark reds near the surface here. And again, you can see these effects that come in just between the stations, which of course we know are lethal and unreliable. The same thing here in extreme resistor, extreme conductor. And the distortion matrix statistics for those of you who are interested. So it's really it's a challenge, but in setting the parameters for this during the inversion, you've obviously got to understand what kind of things you're after and how much weighting to give it, whether it's important or not. And this requires, a few inversion runs to do that. But getting the right level between what structure you want and you think is reliable and what structure is false and due to an inversion of distortion or anything else is obviously the challenge. And there's no right or wrong answer unless you actually know what the geology is. Okay, so that's it on the distortion side. And Randy has previously given a very long, thorough talk on what we do in joint inversions. So I'm not going to spend much time on that. And frankly, we've been presenting it so often that it's a pleasure not to have to do so. But there are some other features within the code, in this code, but also in Carsten's that we'd like to remind you of. And this is where you have known geology and how you can include that within the inversion. So if you have sharp boundaries that you know can be represented by a horizon. So like depth of overburden, particularly in places like Australia, or faults. You introduce these as 3D grid surfaces, and you can try at various positions of those and invert for those. And essentially what it does is we introduce a regularization discontinuity at that surface, whether it's horizontal or vertical. There just happen to be faults from the vertical end and not otherwise. It does require that you know where they are. I suppose the ultimate. Well, let's see what happens in the first place. So this is a straight blind inversion. You can already see, and again, these all start from a half space. And this is a copper porphyry deposit. No guesses as to where that is, and you can see. We know there's overburden in there, and you can see that's doing a reasonably good job of recovering that overburden. But the hope is, of course, if you introduce where that boundary is, you then improve the results below that. So the kind of information that was available, it were 2 layers for the overburden, and then some fault positions, which of course are then updated, down the road as more information comes in from drill holes and so on. But they've done quite a lot of drilling, and then the faults themselves don't have to be continuous. So you literally make them as long or short as you think is reasonable. And these things, very rarely go on forever, or if they do at depth, they tend to be listric and flatten out. We can also do that, of course. So the couple of inversions. The first one is going to be with the blind one you see on the left, and the second one will be the inversion just using the overburden at the beginning. So we fixed the tertiary cover. We've let it change a little bit, but not too much. And that's somehow sharpened up the area, the anomalies below that, not a huge. We've put the faults in here. They're just shown in this image. They're not used in the inversion yet. And then a final inversion run where we do use the faults as discontinuities. And this is where the effect is really best seen. And it focuses up this conductor between it. Now, again, it's starting from a half space. You're not telling it to focus it in that area. And I suppose if you put your cynical hat on, you'd say, well, perhaps we need to actually run some tests to see what happens if you just start with an ellipsoid intersected by these two. Does it then focus it up without knowing whether or not these things are discontinuous or not? So could make some other efforts on that. And we've introduced this same concept now to joint inversions. You'll have seen some of these. You will have seen those for results from gravity work with MT, particularly in graben areas, geothermal systems on the Sumatra fault and so on. And you see similar structures coming in there. And what's nice there, of course, is that the gravity response laterally, the gravity responds much better to lateral density contrast than it does to vertical ones. So it's particularly useful in areas where you do have density contrast across faults like the grabens there. Okay, I said I wasn't going to say very much, and I'm not. This is just a reminder of the kind of things, what we're being forced to answer. So people are saying, well, we've got this data available, can you integrate it? And we're very bad at saying no. And then you find out you've got to do something about it. So through time, we've come to deal with all these different types of data. We use these to influence how the inversion works in different ways. And we're not going to go into the details of that, but just a reminder. So one in its simplest form is cross gradient joint inversion implementation is just promoting a structural similarity between 2 different geophysical domains. Today, we're now doing it with 3. So it could be magnetotellurics, gravity, and travel time tomography. Again, all in 3D, all of the different weightings. We can also use geological data to steer the inversion model gradients. So if you have dip and strike information, for example, we can put those in as tensors and use that to steer the information near the surface. You could then down weight it as it goes deeper. We can also use structural models, whether there's 2D or 3D, and test between different structural models to see whether the gradient fields that you derive from those structural models make sense in terms of fitting the inversion output. So the response from different models that are imposed on the inversion will be different. And you can have a go at seeing whether some structural models or the variations of that are better or worse, sorry, in agreement with the observed geophysical data, whatever that is. And it could be obviously in its joint form with MT gravity or mag or anything. The other one, more tuned for oil and gas, of course, is using the seismic, the best of the seismic data, which is, of course, a structural constraint, without doing an interpretation on it, but just by extracting these structural tensors from the PSDM in this case, and using those to guide the gradient field within the inversion. And that works really well for things like marine CSCM. It's pretty much the only place we've tried it so far. And finally, what's not necessarily easy to do because it's difficult to set up, but where I think most of the work will be going down the road is where you're actually going to test different models, as we said before. So there's one down the bottom there that was published in several forms in 2018, 2019, I think. And then you see down on the right-hand side the different gradients. So the models, the white lines are the different structural models imposed as a gradient. And then what happens to the inversion as a consequence of that. And you look at different RMSs and so on to see whether or not these structural models make sense or not with respect to the observed geophysical data, whatever that is. So just some ideas on this, the one of the structural similarity. I just want to show you, the things that can go wrong. Now Randy, I'm sure included this, and we've presented it several times. So let's go back a step. So we do the single domain inversions first. So MT on its own, gravity on its own, and the resistivity and density cubes are cut through here in a section. And the density is always in the wrong place vertically. It's more or less in the right place horizontally, and we'll see why that is in a minute. But of course, density is the gravity is less sensitive to depth than the MT, which is frequency content as well as the aperture. So when you look at a joint image, you're saying, well, I think the geology, the high density area should be the same as the high resistivity area. It's an intrusive body stockwork at the base of a geothermal system, the reservoir. And there are reasonably resistive lavas. They might be dense or not. And then there's this clay in the center, which will have medium density, not necessarily terribly low, but it's certainly not going to be very high. And then the highest densities, as I say, within the core area where it's high grade alteration, and you have much less porosity and some intrusive material as well. So what happens when you do cross gradient joint inversion? Again, just simplest form, promoting structural similarity between them. So the idea is you come up with a density model which has the same gradient field as the resistivity model and vice versa. And because of the two methods, the one that is stronger, if you like, and again, there are different weighting constraints given, but the one that has more information, of course, is the MT. But the gravity is useful, particularly for lateral density changes. And so you do see a change in the resistivity in that core area, particularly on the flanks here. It's a lot steeper. It may not look it, but it is a lot steeper, and that's just responding to the gravity anomaly over the top here. When you look in detail at what happens to the rest of it, you see that this area here of low resistivity corresponds to little nuclei of higher density. So although the structure's similar, it's coming up with areas where it thinks that this clay here is somehow higher density. And there's this low density area in the middle here, and then it goes up above it and so on. And that's probably not terribly geologically reasonable. So the overall picture is correct. The RMS is slightly higher because, of course, if you're promoting structural similarity, you do end up with less structure in both of the methods. And so the RMSs will be higher. But you've also got stuff in the wrong place above it. So it's fitting it and it's getting the main feature in the right place. But now you've got to explain away, what's causing these density anomalies here. And it's probably that this higher resistivity part up here really is a lot higher density and so on. So down the road, you've got to find a way of actually steering it to be a bit more intelligent, divide the thing into zones and so on. And at this point, you end up falling into the trap of telling it what to do, whereas what we've done so far is entirely data driven. There's no a priori model. There's just simply a request to be similar. Okay, and then you can add the porosity model. So the other way was this, again, testing, in this case, a reservoir model, which is the only sort of 3D models they have, the 3D reservoir models. And one of those parameters, of course, in geothermal is porosity. So the porosity is a proxy for a concept geological model. So high porosity will be low density, low resistivity, and vice versa. So we thought we'd try and test whether that reservoir model was consistent with the observed geophysical data by imposing this as a reference model in that cross gradient constraint on the inversions, simultaneously resistivity and gravity, but also gravity and seismic tomography. And let's see how that got on. That's the model on the left-hand side. You have to come up with a slightly smoother version to make it the cross gradient would work, of course. So here we are. This is the joint inversion of the resistivity and density on its own. This is a different cross-section to what we saw before, but now we're trying to honor the contour lines, which are the porosity. So it's in decimals of 1. So 1 would be 100% porosity and so on. So this is 5.5% contour line here, and then it's much lower, of course, as you get into this intrusive body below it. And as you might expect, the density and resistivity have no problem matching each other, simply because the density is so weakly constrained by the gravity. It gets it correct in the lateral position, but in vertical, it'll basically do what it's told, which is nice because it comes up with a good story. Now, when you do it with velocity, and this is VP, you get a similar story with VS. It's not shown here, but now it struggles. So there should be an obvious match, obviously, between velocity and density. There's a strong density component in there. So why don't they match? Is there something wrong with the tomography that we're doing, or whatever? And it turns out there's a simple enough explanation, is that it's not just the geology we're looking at, but the velocity is extremely sensitive to the fluid type. And this reservoir is steam dominated and not liquid dominated, which is what it is outside the reservoir. So if we go back to, the top reservoir would basically be at the base of this conductor. Everything inside that, this low anomaly here, is probably just related to the fact that it's steam dominated. So although the porosity is not very high, 3.5%, 5%, it's the fact that the fluid is gas and not liquid has a dramatic effect on the velocity, and much more so than it does on either density or resistivity. So you've got to be a little bit careful about, firing all the data in and expecting it all to behave, because the underlying geological premise doesn't hold. So you need to include the entire response, which is, of course, coming from the complete Earth response, which includes, of course, all the lithological alteration, fluid types, and so on. What are we doing in other areas? This is just slightly outside of MT. We do a lot of work in monitoring geothermal, as we mentioned, and we're now recently married time-lapse gravity, which of course is sensitive to mass change in the reservoir. And this has been known for years. It was our attempt at doing this many years ago for Star Energy way back. And recently we've been engaged with them again to do 4D inversion of gravity and time-lapse phases of travel time tomography. And this has been fascinating. going to take a while to publish, but we should have something at the Stanford workshop next year. This is Randy, if he's still online, to complete and write that one up, because it really is an interesting story. We can't show it here, but this is a pretty exciting development. There are parallel efforts using MT for monitoring. We're not involved in that. Finally, we've been wittering on for an hour now, so it's time to wrap up. But something on inversion uncertainty estimates. We appreciate that as you go, again, going back to that scene from the boardroom, or an asset team that's trying to make a decision on abandoning an area or whatever, whether that's in mining, geothermal, or oil and gas, doesn't really matter. It's the same discussion. You come up with a geophysical model and they say, well, what's your uncertainty of depth to basement or depth to target, whatever it is, and you just pluck the thing out of the air and say, well, it's 5% of the depth to the thing, or 10%, and they just sort of look at you. Is there any science in that? And there have been a lot of efforts on trying to come up with reliable uncertainty estimates. And we've had to go at some of our own in the past. This is some early work, 2012, almost 10 years ago now. We did some work with Mike Thompson, actually. And you can see the kind of results that come in at the bottom. You're working in an equivalent space in 2D only here. Very quick to produce forward solves that, of course, and you come up with a population. And you can get probability maps out of those. You can see those things on the right-hand side. It turns out, of course, it's pretty hard to do this in 3D as well, but that's, it was a reasonably promising approach. Things changed. We changed ownership at that time. Anyway, there was a focus on something else. And we came back to revisit it a few years later, looking for something at the top of the page rather than the bottom, because easy and hard. Hard, we knew Bayesian inference and models, and we'll have a look at some of that. But I'm just going to go through this very, very quickly. We tried a most squares analysis. We started working with Max Major's group in Petronas, and we got a chance to do some of this work together, which was great. Ultimately, it's probably not the solution, but we'll go through and see what we had. Some of you, again, may have seen this already, but it's just an idea of some of the other things we're working on. Let's get through this and see some examples. Right, so here's first of all an example for the synthetic model, and point here is we have a least squares model shown in black as an output, and the starting model. There you can see the true model should be the green one. Okay, 4 layers over a half space. Now, we're all familiar with that. That's fine. When you do a most squares analysis here, and again, it's not what you see on the screen are the maximum models. So one maximum model in the 1D case. And you see how it overcompensates here in the conductor, and then it shoots out again in the resistive. Of course, we're talking about MT, so the resistive side has less sensitivity. It's done a better job of controlling where the conductors are. And that's all fine. Now you look at it in the most squares bounds area, which is more interesting. That's what the method is for, and you see what, that doesn't mean that you get a solution in that red space or a solution in the blue space. It's just that the possible solutions lie between those two bounds, the blue and the red one. So you think of that area as a kind of gray area in between of possible space where it works. And what's interesting is that it suddenly diverges at some point. And this is essentially a measure of, well, it may not be the most efficient way of getting at it, but it gives you a maximum depth of investigation quite efficiently. And it is a dramatic change where the sensitivity drops off. Okay, and here the envelope models around data fit again. So what those when translated to an MT response are the other lines you see on the data here. Now we look at it compared to other variance estimates, and we this is linearized covariance on the left, and most squares in the middle here, we've seen already. And then we did a Bayesian inference model here, and it's remarkably similar, and that's that's fine. And we thank Ross Brody Geoscience Australia for that. And the it seems to be working fine. That was okay. The problem is when you get to take it into 3D, and although we come up with a solution, we had to actually limit it to an area focus model. So you only want to attack one feature if you can't really attack the entire area. If you're, I don't know, trying to look at a conductor in an otherwise infinite half space, then that's fine. If you've got lots of different geology going on in 3D, which is what happens in the real world, this gets a little harder. Anyway, if we do it for this purpose, we're just going to look at one question: how thick is the resistor in this case, and see what happens. So we go back to our favorite area in the foothills, and we come up with a simplified model of what that is. This is just a cross section through a 3D model, and you can see the kind of sedimentary layering and the overthrusting and how it's represented here. It's a recumbent fold, and the thing we're after is this high resistive body, which are clean sandstones, which are ultimately the gas reservoir. So let's call that the target for now. How do we quantify the uncertainty at this depth, and what kind of examples do we get out of that? So this is the masking function shown here, and now we see the bounds that we get out of it. This is a plane looking through if you top down on it, with just the masking peeking through it. So it's a map, if you like. It's not a view of it sideways. And then the shells here show the least square solution in the middle, and then the bounds that come in that you'd expect from this. So I suppose you could say that's very nice. It's not terribly surprising. So there's this kind of gray area around where your known resistor is. So how useful is that? I suppose just the computational cost wasn't too much, but at the end of the day, it doesn't get away from the problem that you would need to do this, on the entire inversion sequence. And so while we got it working, proved it, that's fine, but we think that actually you'll need a different approach, and most likely that's going to be a Bayesian one. So we'll get back to that some other time. Finally, just another bugbear that we are also working on. This is the eternal question of how you deal with anisotropy and distinguish that from structure in the MT context. So we're eternally dealing, back again, here we are in the foothills, but they're not only this, of course. It would be exactly the same in an area of Proterozoic basement where you've stretched and squashed the crust, and anisotropy will be fairly intense in those parts as well, at various scales, of course, and those matter too, what scales those are. But your regional scale, fold belts and so on, that are metamorphosed and are currently hosting mineral deposits, they will have these effects as well, along with all the other nonsense that happens in hard rock that makes an MT contractor's life a misery. So these kind of typical responses that we get from that. You see this is the response at the top is from the top of the anticline, and then the response out in synclines is on the right hand side. This is something we published with Total way back in 2002 in an earlier life, but and another one here on the right hand side, which we published with RWE in the Zagros Mountains. And there it's even more spectacular because, of course, there's less vegetation. So when you fly over there, if you've taken flights from Europe heading out to the Middle East and you fly over these mountains, it is incredible. Just these great whaleback anticlines and so on that appear. When you get a bit closer to it on the ground, it's even worse because these units here, this is the famous Gaxaran formation. And it is literally looking at a series of resistors and conductors in parallel in sheet format. There are these marls and gypsums. The gypsum, of course, is extremely resistive, the marl not. Gypsum, but also anhydride. As you can imagine, these things at this scale just forming this infinite plate-like anisotropy right the way across it. And we did some modeling, I remember, way back then, but in the field, I've lost the results since then, but just of 2D modeling, trying to simulate what an anisotropy would look like, and we managed to reproduce what these curves, because one curve just disappears in it because there's no response, and the other curve goes flying upwards. But again, the only way that we can look at this is through proper treatment of anisotropy, and we've started on that. We'll get a little bit of that in a moment. And here's another example from later on in a previous life, when we were again looking at the same foothills, a different section. It's not the same area, but it doesn't really matter. The point is, this was a well that was drilled on the edge of an anticline, and it's fairly typical. What they tend to do is they drill it where they can get to. So they can't get to the top of the mountain, but they can get close enough to the base of it. They drill from there and then drill in sideways and arrive at the target with a directional well. And then if that doesn't work, you come back a bit, then do a sidetrack. And the resistivity logs from the sidetrack and the main log were incredibly different, and they forced the logging company at the time, a very reputable company, nothing wrong with the logs in that case. And they redid it. They rechecked the processing and so on, and they basically came back and said, "Look, I'm sorry, but the resistivities really are different." And when you think about it, in a section like that, if you go back to that geology, and it's not the same geology here, but it's entirely clastic in Bolivia as opposed to the carbonates you see here, but you do have hard rock and shale. So you will generate this rock here is clean sandstone, and over above it you've got mixed turbidites and some very conductive elements in there, but also some resistive ones. So if you see it as a vertical anisotropic layer, then these have to influence the usually horizontal empty fields that we're dealing with. And so, when we always see a resistor, this is just a position of the two wells sitting on this blind empty inversion. Again, it's on the edge of something, but it's higher up than where we'd expect. This resistor we would hope would be down there, but it's always been higher up in the section. And I'm guessing there's a reason for that. We've always been able to force it down somehow. You come up with the story as to why it needs to be there. That plot just in the middle just accentuates this as a cumulative conductance plot of the same thing with the wells, following the curves there. So more on that. So I'm going to wrap this up. We haven't covered half the things. I really wanted to talk to you also about the work we're doing as CSAMT, but we can share those publications with anybody, and you may have seen them before anyway. But that's coming out, and we're looking for real data for that, the 3D land CSAMT, looking at both the fields but also the impedances. So what's missing now? And this is a kind of begging, really, to anybody out there. There's lots of people working on these things on and off, but I think where we would see a difference in terms of the reliability of the product that we could sell, so there's a value to it, right, is on data processing, not just getting better signal and so on, signal to noise ratios, but also working on the error estimates that come out of that, so that we can go to use true error estimates. And I know Alan's been working on this in the past, and we've had long conversations about it. But there seems to be, a focus on inversion. Everybody's writing their own inversion codes, and there are people working on processing, but it seems to be less, or at least we're hearing less about it. Anyway, we'd be delighted to hear from anybody who is doing something interesting. And then on the 3D inversion modeling, of course, we need to introduce TTI and anisotropy. There's no question. And then we need to do the tests and see, how important it is, where it's feasible to make it work, and so on. And we have, of course, VTI to anisotropy in there already, and there are other codes that have TTI in it, but they're not really set up for the land MT case. So we'll get on and do that. We're not pretending to be ahead of the curve here. It's just, it's the only way to keep the pressure on this effort of making things geologically reliable. Pragmatic uncertainty analysis, that goes without saying. You know, we'll get there. There are other ways to do it. And I'm guessing we'll do more and more, particularly when it's easier to impose these 3D models and transfer them across and use them to create different concept models to test for their reliability with respect to the geophysical data. So I'm sure there are other things, and there are lots of other ideas in there. These are the ones that came to mind thinking about it earlier on. So we'll you know, we're always glad to hear from other people if they'd like to collaborate with us on that. Some of these things we're working on, we can't work on everything, and we do hope you're those of you who are GeoTools users are enjoying the new function, and the more to come. So thank you all very much, and thanks again to Alan for inviting me, and thank you to all my colleagues, particularly here, Wolfgang, Randy, Wolfgang, Federico, Carsten, Stefano Alice, Mauro, and others. Thanks again.
Yeah, thank you very much, Stephen. That was very interesting. Yeah, I think I could actually, you know, fill the whole Q&A with sort of different questions and discussions about like all the various topics. I found a lot of things you raised. Yeah, very interesting. Since we have already a couple of things in the Q&A, I just limit myself to one topic that you raised, which I've been thinking about recently, which was this, in inverted commas, failed joint inversion with the VP and the gravity, yes, where you say, okay, we do the joint inversion.
Or shall I go back to that?
Yeah, the structural similarity thing, and you know, actually the models are not very similar, yes. And from a classical point of view, you would say, okay, the joint inversion did not work, but I tend to now think of this as actually quite powerful results. And I think you highlighted that, how you described it, because it means that something in the data, yes, doesn't allow those models to be similar in a way that you want them to. And then you need to come up with a sort of explanation. It's maybe sometimes even a more powerful statement, because yeah, actually on this plot you showed, yes, you can explain the gravity data with these high density pockets at the top, but those are probably artificial. Whereas, you know, if you wouldn't be able to fit the data, then that would tell you, okay, there's something there that, you know, doesn't match our expectations. So I find that sort of another side of joint inversion that is quite interesting.
Yeah, it forces you to think, I suppose. You know, it's come up with a solution in the main area, and the eye is drawn to the great big, you know, black hole in the middle. But the details around it tell you there's something else going on, as you say. No doubt you've got a solution for it, Max.
Sorry?
No doubt you have a solution for it.
No, it's just, I mean, I think it's like, I just don't think, or as you explained, I think it's not a failure yet. It's
No.
a sort of, it doesn't match your expectations. So then you need to sort of think about alternatives, or
absolutely,
the result. Okay, let's move on to the Q&A. The first one is by Pavel Alexandrov, and I saw this earlier. I think, Pavel, you need to explain a little bit more. I just going to read it, and then yeah, maybe you can elaborate. The impedance of the lower half space, and I'm not sure which half space he is talking about, is associated with the electromagnetic parameters of the geological environment in the cases of sources located in the upper half space. So I think this needs some clarification of, you know, what is lower half space, upper half space? Are you talking about air and earth or something? However, if there are sources in the lower half space, the impedance will be associated with the electromagnetic parameters of the upper half space. How to invert?
I'm sure he's right, but I'm delighted to see Alan has said he'd like to answer this question live. So I can't resist in this case. Pavel, are you still on the line? I guess it must be.
I think maybe he will be writing something about this. I suppose it's related to the electric trains example, if he's talking about sources like in the air and in the earth, but maybe he can clarify this. Okay. Or do you want to say something about it now? And
I honestly don't understand the question, to be honest. I'm not
yeah, okay, then let's move on, and then we'll maybe get a clarification. So Dennis Woods says, why is instrumentation not a focus of your group? You must have had occasion to think what we could
well,
better.
That's fair enough, Dennis. No,
instrumentation is the question.
Well, fair enough. I guess I didn't want to be seen to be promoting one instrument over the other. You know, we've used all sorts of different instruments in the past, and I'm not going to get into that. There's been a clamor for cheaper and more EM receivers that you could use for MT. And we got involved in many of those discussions with several of the manufacturers, and include Phoenix Geophysics, but also Metronics, of course, and Zong in this case, and there are plenty more out there. They may be coming into it. But I don't know that that's going to answer very much. I mean, yes, it would be nice to have more equipment and to be able to lay out more equipment cheaper, but you're still going to need to work on things like electrical contact near the surface, which tends to be a bit of a problem, and all the issues around, you know, siting and permitting and so on. You need to get on the ground. There are some advances in the airborne part, but of course that's not. It's just the magneto part without the tellurics. So you're right. I haven't talked about instrumentation, and we might have done if we were still in the acquisition business. But while we'd like to see more receivers, it's really not. It's not easy. You've got enormous dB to deal with. So the dynamic range is just much higher than people go on about. Well, you know, if seismic can cost $10 a geophone, why can't the MT equipment be cheaper? And it's just dealing with completely different things. It's just not that simple. I guess the question would go back to the instrument providers, but I know they're going to, you know, we've heard their answers before. Alan's been badgering them for years too.
Yeah, and I mean, so Dennis says, thanks, that was exactly what I wanted you to talk about. And okay. I mean, one of your comments that you made about the cost of the instruments versus sort of everything else, the effort, reminds me of an article I once read about sort of people saying, okay, we can make a gravimeter that is, you know, 100th the price at maybe sort of a little bit less sensitivity. So this is going to change sort of gravimetry forever, to which I thought, okay, well, you know, the leveling and the positioning and all these things. Yes.
Well, the people time on the ground, and
exactly,
and the safety aspect of that too. You know, there's more and more requirement from industry, and it doesn't matter which industry that is, to reduce boots on the ground. So
yeah, and
drones,
and for that,
airplanes, whatever it is, and of course you can't do seismic from the air yet. You can't do MT. As complete MT, you can't do that from the air either. But if they could, they'd just do that. You
know. Can I just jump in and advertise Adam Schultz's? Adam Schultz's EMinar on the 16th of February. Faster, lighter, cheaper. Developing new instrumentation to broaden access to MT.
There we are.
So Adam will be directly addressing this, and then we have Ian Ferguson on 9th of March talking about MT instrumentation generally. So those of you who are listening who are interested in instrumentation, make sure you catch those.
You haven't managed to get some of the actual manufacturers involved, have you? People like Jan and Bernhard?
I've tried. have tried, yeah, but I think their talks might be rather one-sided.
Not like the rest of us, Alan.
No, not like yours, son. Stephen.
It would be good. Well, maybe some webinars where you've got a couple of them battling away at each other. That would be entertaining too.
Well, we have planned for the very last webinar is an open mic, and we're going to invite anybody who wants to speak. And so perhaps that would be an opportunity to get
absolutely
instrument manufacturers to jump in and say something.
Yeah. All right, there's a question there from Tyler Mathiasons. So
yes,
to what extent does your group integrate information not provided by your clients?
So basically, I think the question, the idea is, do you do your own research and say, oh, listen, we found this sort of, structural map and we've integrated that into your
We do.
version.
No, that we did. We do if it makes sense. We try to avoid doing things for free, I suppose, is the bottom line. So if it makes sense and the client is happy with the idea of doing that, then that's usually, you can find that stuff out before you put a quote in. And these things are always open-ended. To come up with a bit more data, you throw it in, and that's fine. If you come up with an entire new set of structural models to integrate, then if you haven't factored that in at the beginning of the proposal, then that needs to be usually a separate item, because it's quite a lot of work. But the answer is yes. We'll integrate whatever's available, what makes sense. And the making sense means, on both sides, from our side, but also from the client side. So we've integrated. We did some work, some airborne work in Alberta, and it's a well-organized place, of course, and there are these wonderful 1 to 50,000 maps digitally available, and they have tips and strikes on them. So those images that you saw earlier came from that, and there you are. That one there, tips and strike, that comes from an Arcan. It's an area called Lovett. And we did that. We used that data directly to influence the near-surface resistivities. It was a 3D inversion of a Hallinan and a frequency domain airborne survey. That's been published. So actually, send us your email. We'll send you a copy of that. Karen, nice to see you. That's great.
Yeah, so the next question is from Karen Christopherson. If you're given a data set to 3D invert and some data have HVDC effects or distortion in them, what do you do? How do you handle those data for the inversion?
Thanks, Karen. You know the answer to that already. You basically today need to mask out the data, and that, which doesn't make any sense. And it's a very good provocative question, because we ought to be able to treat those within the model. So the effects are going to be seen in the model, and they're obvious in some cases. Usually you see it in the tipper as this. Because what Karen's talking about is not the active noise source along the high voltage DC lines that have a plague in the Western US, but the fact that they're a passive conductor. And so you see these things, particularly in the tipper data. Now, it's not enough, obviously, just to remove the tipper and say, well, I'll invert the rest, because if the distortion is seen in the tipper, it is, of course, by default, it must be in the other component too. So rather than just masking all the data out, around it, this effect will be seen in all the data. It just becomes weaker as you go away. It's not. So we don't currently have a way of modeling that within the inversion, but that's something we're getting badgered to do. I think we'll be close to it in a year's time. We're changing the way we're doing fine meshing and so on. So we should have a way to do that. There's a bit similar thing people talk about, can you handle casing? Can you handle surface infrastructure, which is in contact with that? So pipelines that are in contact with the ground, whatever other power lines they're grounded, that kind of thing. So we handle it by brute force, and that's not very satisfactory.
Yeah, and I think you have to also be careful in the interpretation of your models, right? If you see certain structures, is that geology, is that infrastructure, and how can you distinguish?
Yeah, absolutely right. So you plot all the infrastructure on at least some of your interpretation maps, so you can see that people are aware. Look, here it is. Any associations are to be treated with a grain of salt. Yeah.
Yep. Well, that seems to be the questions from the audience.
If I can just ask one, Max.
Of course.
Yeah. Yeah, Steve. Well, I can't write it because I'm a bloody host. Steve, when you do these inversions that are guided by faults, how wrong will the model be if the geologist got the faults wrong?
They'll be completely wrong.
Yeah.
So this is showing a static thing. Geologists are very trustworthy people, by the way, but they then get updated when another geologist comes along and drills another hole, and so the faults come and go. Ideally, you would want to have a scenario, and again, we've thought about this, and everybody screams back at me and says it's very difficult. And I say, well, that's good. It's difficult, because if it was easy, everybody'd be doing it already. But to invert for the position of the fault or the discontinuity, whatever it is, so rubber sheet type discontinuities, but as tear surfaces and not just they must be discontinuous. Embodiments so far have been these continuous horizons and so on, sheets, but it's not easy, and you've got to have got to limit the number of them and so on. The alternative way of doing it is just to run a suite of chain and just see what fits the data better. And again, that's that's anyone's guess too. What one man's good fit is another person's not. So you change the position of the faults, or you change how impermeable they are, and so on.
Yeah, and I mean, I've thought about this a little bit, and the way I at least so philosophically treat it, it's more like a hypothesis test. Yes, if the faults are in this position, what will the model look like? Yes, and then you need to look at other information and say, yeah, all right, that model looks quite reasonable and matches with other things that we think we know are true. So it's maybe better, but yeah, at the end of the day, the model itself will just produce this continuity where you tell it to, right?
It doesn't. It's smoothly varying on either side of that equally. It doesn't. You don't give it any information except that you can put, if you want it, there's a discontinuity here if you want to use it. And the question would be, you start to do a synthetic model and see if you put a continuous ellipse across that, and you put the faults through it, but there's no break or offset at that fault. When you do the inversion with the fault present, allowing a discontinuity, does it then just focus everything up together? In other words, is it biased to focusing? We need to do that test.
Just one other quick question. Have you ever done any almost near real-time revisiting of the inversions, in as much as I've tried to push our clients to allow us to reinvert models during drilling to try and guide drilling better. But as soon as the drillers come into camp, the geophysicists get thrown out, and it seems like we're missing an opportunity here to update our models during drilling.
Yeah, we do that quite regularly. Drilling is a lot faster in mineral exploration, of course. So by the time they've drilled it, they're gone or they've moved on. But in the oil and gas, these deep wells that we were seeing, I can't remember where we are, but anyway, this model here, the structural model in the middle, they can take 6 months to 8 months to drill, particularly if they've got sidetracks, and they cost an absolute fortune, $60 to $100 million to drill a well. You've got to build a road in there. It's a nightmare. So yes, they're very interested, and we've done surveys actually. We tried to, I think we thought about patenting it. It's called MT well drilling. Yeah, it was a ridiculous idea. We were just there doing a 2D line, which happened to be cut for a seismic survey, so it was quite easy access. And then the 2D models were being done in the field in real time and sent off to the client. And that actually worked. It was never published. It's a pity, but it worked. It provided enough general location to be able to tell them to sidetrack in one direction or another. It was a really straightforward decision, but a very, very expensive one to get wrong. And it gave them enough information to say which direction to do it in. Now they'll pretend they didn't listen to us, but it actually ended up in the right place, and they hit the target. It turned out to be an enormous gas field, but it was. I guess we don't do very many of them. I'm trying to think of another one. I can't. That was way back. Yeah. Is that the kind of thing you were after, Alan?
Yeah, exactly.
There are then, look backs. So some work we published recently with Mike Hoverton and Chevron, a look back at Lona, which of course has been endlessly revisited about the CSEM modeling they were doing there. There was some MT data there too, processed from the CSEM data. And there again, it was the eternal struggle, trying to look back and see, okay, well, if we knew this, would we have done, would the drilling decision have been made differently and so on. But in a lot of those cases, the companies have moved on, the blocks being dropped, and they just say, yeah, go for it, whatever turns you on. But it doesn't have any impact because, of course, they've gone.
Yeah, I think that's, of course, in the commercial business, yes, it's always a bit of the issue. Yes, once the commercial decisions have been made, then the academic interest isn't really there. Yes.
Yeah, but it's a perfectly valid educational process, which is kind of why we did it. It was informative to the method. To if we'd done it differently at the time, integrating the seismic with the CSEM as we do. You see this image here in the middle left on the right. That was used as part of the process, and it turned out that helped. That they might not have made the same decision had it been. But again, it becomes cross between geophysics and philosophy, which is pretty dangerous terrain.
Yes. Well, I think we had a great discussion, and I'm sure, if people have more questions, they can email you or, look at the papers. You quoted quite a few.
Yeah, if anybody wants copies of papers, so do get in touch. The email address. My God, did I not put that on? No. Anyway, thank you all for listening and staying with it. Let me just get to the last one. Just there, the one is just my name at cdg.com. So do get in touch. Be good to hear from you all. And visit the career thing. You never know. Yes,
certainly those who are looking for a job or might be looking for a job, it's always a possibility.
Particularly if they have a new processing code, even better. All right. Thank you again, Alan and Max. That's great.
Yeah, thank you very much. And everybody else, remember next week we have Hannah Peterson combining land and lake bottom MT for the Mono Basin in California. So with that, have a good day or evening wherever you are, and see you next week.
All right. Bye.